Hello, this is the lecture for linear equations in two variables. I'd like to start with a review of graphing. When we graph points and equations, we graph them in the Cartesian coordinate system. Okay, the Cartesian coordinate system is simply a grid that is split up into four quadrants, 1, 2, 3, and 4, by an x-axis, horizontal, and a y-axis that's vertical. These two axes meet at the origin, and every point in the Cartesian coordinate system can be identified by an ordered pair. The ordered pair will have an x-coordinate and a y-coordinate. The x-coordinate measures the distance of that point from the vertical axis or the y-axis. The y-coordinate measures the horizontal distance measures the vertical distance from the x-coordinate or the horizontal axis. The origin, of course, has the coordinate 0, 0, because it has no horizontal displacement from the origin or from the x-axis and no horizontal displacement from the y-axis and no vertical displacement from the x-axis. All right, so I mentioned that when we plot points, they have an x-coordinate and a y-coordinate. Let's look at some examples of plotting points. If we have the point 3, 5, the x-coordinate is 3, the y-coordinate is 5. So to plot a point, we always start at the origin, all right? And then we count 3, in this case, 3 units to the right because 3 is positive. So x is measuring the distance from the vertical axis. So we want to move in the positive direction. That would be to the right, 3 units. 1, 2, 3. The y-coordinate is 5. It's positive 5. The y-coordinate measures the vertical displacement. So we would want to count up 5 because 5 is positive and up is the positive direction vertically. So 3 left, 5 up, 1, 2, 3, 4, 5. Here's the point, 3, 5. Right? When the coordinates are negative, we're going to move in the opposite direction. So to plot the point negative 2, 1, the x-coordinate is negative 2. Horizontally, negative is going to be left. So we start at the origin. We count left 2 units, 1, 2. The y-coordinate is also negative. So we would go down 1 because the negative direction vertically is going to be down. The coordinates at this point then are going to be negative 2, negative 1. Okay? What about if one of the coordinates is 0? This third point here that has the coordinate 6, 0. Well, the x-coordinate is 6. When we start at the origin, it's positive 6. So we'll go to the right 6. 1, 2, 3, 4, 5, 6. There's no vertical displacement, though. The distance from the x-axis is 0, so we just stay right there on that x-axis. The coordinates of this point then are 6, 0. Okay? Negative 4, 5. X is negative 4. So we start at the origin. We count to the left negative 4. 1, 2, 3, 4. The y-coordinate 5 is positive, so we'll go up 5. 1, 2, 3, 4, 5. Negative 4, 5 up there in quadrant 2. 1, negative 3. Here we've got an x-coordinate that's positive, so we'll go to the right 1 unit. The y-coordinate's negative, so we'll go down 3. Here's our point 1, negative 3. And then lastly, 0, 2. Here our x-coordinate is 0. So we have no movement horizontally, right? There's no distance from the y-axis. We just stay right there for 0. But vertically, we need to go up 2. So right here, we have the coordinate 0, 2. All right? A couple of things to note here. When the y-coordinate is 0, the point will always be on the x-axis, right? Because there will be no vertical displacement on that horizontal axis. When the x-coordinate is 0, the point is always going to be on the y-axis because there's no displacement from the vertical axis. There's 0 movement left or right. Okay. Also note that in quadrant 1, over here in quadrant 1, all the coordinates, all the points that are in quadrant 1 are going to have a positive x coordinate and a positive y coordinate. In quadrant 2, your x's will all have a negative value. Your x coordinates will all be negative, because look, we're always going to be left of the vertical axis, the y-axis, and your y coordinates are always going to be positive, because quadrant 2 up here, all the y's are going to be above the x-axis. Down here in quadrant 3, of course, x and y's will both be negative, right? All of the x coordinates are left of the y-axis. All of the y coordinates are below the x-axis. And finally, over in quadrant 4, your x's will be positive because we're right of, or we're in the positive direction of the y-axis. And your y coordinates will be negative because we're down in the negative area vertically, right, or below the x-axis. All right. When we graph linear functions, they always graph to a straight line, okay? Here's some examples of linear functions. This linear function could be written algebraically, and I'll give you a little peek ahead. We'll be doing this shortly. If I were to write the equation for this particular graph, it would be y equals x plus 4. Well, that's not right. 2x plus 4, sorry. Y equals 2x plus 4. This is just a horizontal line, y equals 2. We don't even care about x here because x could be just about anything, but y is always 2, so it'll be y equal 2. This one is going to be y equals negative 3/4 x plus 3. More on how I wrote those equations later. All right, slope is a very important concept with linear functions. Slope can be thought of a number of different ways. When we have the graph of a line like we have here, slope measures the slantedness of this line. We can also think about this as the rate of change between 2 points that are on this line. Okay, various ways you'll see slope represented. We usually use the letter m to represent the slope, small case m. And we can think about that as the change in the output over the change in the input of a function. The output of the function is going to be usually the y value and the input the x value. So we can also think about that as delta y over delta x. That just means the change in y over the change in x. Delta is just the Greek letter that represents, it means the change in. As a formula, we could write it y2 minus y1 over x2 minus x1 if we know the x and y coordinates of 2 points that are on that line, point 1 and point 2. And then lastly, we could think about it as rise over run. We're trying to find the rate of change between 2 points. We could count it out, rise over run. Rise would be the vertical movement to get from one point to the other, and run would be the horizontal movement to get from one point to the other. So if I wanted to find the slope of this example here using rise over run, I start at 1 point, and then I count how many units do I have to go up or down to get to the second point. Well, if I'm starting at this point and I want to get to this point, I'm going to need to go up. Let's see, these are divided by 2, so I'm going to need to go up 1, 2, 3 units. So the rise here is 3. I went up. It's positive 3 because I went up. The run then, to get to that point, the run is how many units horizontally do I have to move? Well, I've got to go to the left 1, 2, 3, 4 units. Since left is the negative direction horizontal with x's and horizontal, I'll say that's negative 4. The rise over run is 3 over negative 4, or I could think about that as negative 3/4. Okay, That's probably the easiest way to find the slope of a line when you have the graph in front of you and it intersects some whole numbers. I can also use the formula, though I can always use the formula, the change in the y values over the change in the x values. If I use the formula here on this example, I want to say it's y2 minus y1 over x2 minus x1. Let's see, which point is y1 or is point 1 and which one is point 2? It doesn't matter. I can decide either one. Since I started with this 0.44 when I was doing rise over run, I'll let this be my x and y coordinates. So my x1 will be here, my y1 will be there, my x2 will be 0, my y2 will be 7, right? So then to find the slope with the formula, y2 minus y1, y2 is 7, minus y1, that's 4, so it's 7 minus 4 over x2 minus x1. x2 is 0, x1 is, of course, 4. 7 minus 4, that's 3 over negative 4, or negative 3/4. All right, a couple more examples of finding the slope. Here we don't have the graph, so rise over run isn't going to be that helpful, is it? But we can always use the formula. The slope is the change in the y's, or y2 minus y1, over the change in the x's. x2 minus, oops, that's a 1, minus x1. Right, our change in our y's here. Let's see, we need one point to be x1, y1, the other to be x2, y2, and it doesn't matter which one. Maybe I'll just let this be x1, y1 since it appears first. And then I'll let 4, 8 be my x2 and my y2 since it appears second. So y2 minus y1, that's going to be 8 minus 6 over x2 minus x1, that's going to be 4 minus 3, or 2 over 1, which of course is just 2. Okay, one more example. Find the slope of the line that passes through the points -3, -7, and let that be our x1 and our y1, and -9 and 1, and let that be our x2 and our y2. So the slope here, then y2 minus y1, that's going to be 1 minus y1, -7. Be careful with that. We're subtracting a negative, so we need parentheses. Over x2, that's -9, minus x1. x1 is -3. Okay, so 1 minus a -7, this, of course, is 1 plus 7, minus a negative. We kind of turn each other into positives, right? And then -9 minus a -3, that's -9 plus 3. So 1 plus 7, of course, is 8. -9 plus 3 is -6. Well, that's going to reduce down to 4 over -3, or -4/3. Okay. Look at these two examples. There's something interesting about them. In this example, look, the x coordinates are the same. They're both -3. What does that mean? Well, let's calculate the slope. Let's calculate the slope with the formula. Let's try that. x1, y1, x2, y2. Let's see what we get here. So our slope here then is going to be, I'll just write it one more time, y2 minus y1, change in the y's over the change in the x's, 8 minus 5, our y2 and our y1, over -3 minus -3. Okay, well, that's 8 minus 5, that's 3 divided by -3 plus 3. Well, that's really interesting. That's 3 divided by 0, isn't it? What is that value? 3 divided by 0. Can we do that? Can we divide by 0? We cannot. We can never divide by 0. That sort of blows up the universe, right? How many times does 0 go into a number? I mean, 0 isn't even a value. It's a lack of value, right? We cannot divide by 0. So this 3 divided by 0, we have to say that this is undefined. Undefined. It's an undefined slope. So when you're calculating slope and you end up with a 0 in the denominator, we want to say that's an undefined slope, because you can't divide by 0. Now look at the second example. This one's kind of interesting as well. This time, look at this, the y coordinates are the same. The y coordinates are the same. So if I had to calculate the slope, my change in my y's, it's going to be 0, right? Over 8 minus 3, or 0 divided by 5. Now, is that okay? Can we divide some number into 0? That's okay. That's not undefined. But, of course, 5 does not go into 0. Nothing does. So the answer here is 0. Right? So sometimes the slope is a number. Other times we're going to have an undefined slope. And then other times we might have a slope that's 0. When we have an undefined slope, I will show you shortly, this is going to be, when we graph it, it's going to be a vertical line. When we have a slope that's 0 and we graph it, it's going to be a horizontal line. More on that later. All right, let's take a look at slope in an application context, right? Or, we know now that the slope is the change in the y's over the change in the x's. It measures the slantedness of the line, and that we can think about it as a rate of change between 2 points on a line. But we can even expand that. Slope as a rate of change, it can be a rate of change even when we don't have a perfectly linear function. Look at this example here. This is a growth chart for a child. You probably have seen something like this before. Every year a child comes in for their physical to the pediatrician, and the pediatrician records the child's height. So on the x-axis we have age, and on the y-axis we have the height in inches. All right, even though this is not the graph of a linear function, it's not a straight line, we can think about it as an estimate of a linear function, right? It's almost linear. So we might imagine a vertical line like this, and that's pretty close, right? Some of those points aren't on that line, but some of them are, and that's sort of an estimate of a linear function, right? The rate of change of that line is going to be the same always, right? But in reality, the rate of change isn't exactly the same for this particular child when they were growing. But we can find average rate of change, right? The average rate of change, it's going to be the slope of a line between 2 points in this series of data elements. So here we want to find the average rate of change in the child's height between the ages of 2 and 6. 2 and 6. Well, we can use the slope formula for that, right? We know the coordinates of these points. Well, I think we can. Look here, when the child was 2, looks like he or she was 31 inches tall. When the child was 6, follow that up there. So when the x is 6, the y is 40. So when the child was 6, they had grown to 40 inches tall. So what is the average rate of change here? What's your change in your y's over your change in your x's? Right, so when we think about it. Or in this case, we'll use a formula. We'll say it's y2 minus y1 over x2 minus x1. That's going to be 40 minus 31 over 6 minus 2, or 9/4. Let's see, as a decimal, that's going to be 2.25. Now, what does this mean, though? That's the number, that's the slope, that's what m is equal to, right? 2.25, but what does it mean? It's an average rate of change. It's 2.25 numerators per denominator, or 2.25 inches per year. Okay? All right, so that's what we just did. We just measured the slope of the line between x equal 2 and x equals 6. And that one pretty exactly followed our estimate, didn't it? Our sort of linear line there. But if we take a look at the average rate of change between 13 and 16, let's see where that is. Might not be the same, right? What is the average rate of between 13 and 16 look like? Let's see if I can put that on here in orange. 13 is here. Okay. 16 is here. That one has a different slope, doesn't it? The slantedness of the orange line is different. It's kind of to see because I didn't draw it very well, did I? But it's different than the slantedness of that pink line. It looks like it might be a little bit steeper. Let's calculate it. Let's see what it actually is. Well, the coordinates of 2 points, let's see, at 13, this child was 52 inches. And at 16, this child was 62 inches. I think that's what that is. All right, so the slope 62 minus 52 over 16 minus 13 is 10 over 3, or about 3.33 inches per year. Okay, so larger slope, that means it gets steeper between the ages of 13 and 16. And that makes sense, doesn't it? Yeah, because in puberty, most children take a growth spurt, right? And you can see by the data here, there was a big growth spurt between the ages of 13 and 14. All right. So linear functions can be very valuable. Slope is how we evaluate the rate of change. Of course, with a child's growth, rate of change in height, growth rate, right? The growth rate is really important. If a child isn't growing for some reason, that can indicate that there's something wrong, right? Something medically that needs attention. Let's look at another application. Okay, here we have a population of a town is declining, or it's declined. Back in 1990, the population of this town was 60,000 people. But by the year 2000, the population had declined to 58,000. Well, if you're the mayor of this town, you're very interested in that rate of change, aren't you? Because if that rate of change continues, eventually the town's going to have 0 people in it. And 0 people in it. And of course, it's going to affect the tax structure and everything else that depends on population. So let's see. Can we find the rate of change in this population? Well, we know that we can use the slope formula. Slope is rate of change, right? We can use this slope formula, y2 minus y1 over x2 minus x1, if we know 2 coordinates on the graph of that, like if we were to graph this, or if we know, two sets of inputs and outputs, right? Well, let's see. I think it's dangerous to calculate with years because they're measuring time, they're measuring the number of years since the year 0. But in this case, when we're looking for rate of change, we're only interested in the change in those years. So that should be fine. So I could consider the coordinates of this first point to be 1990. So in the year 1990, or my independent variable, my x, is 1990. In 1990, the population was 60,000. Okay. So the population was dependent on the year. So y, or 60,000, would be my dependent variable. And typically that's the case. X's are our independent variables, or given an x, we find a y. Y is the dependent variable. And then again, we know here that in 2000, that population had declined to 58,000 people. Right? So we could consider this an x1 and a y1 and x2 and a y2. And I think we can calculate that rate of change using the slope formula. So we'll have 58,000 minus 60,000 divided by 2,000 minus 1990, or negative 2,000 divided by 10, and that'll reduce down to negative 200. Okay, so what does this mean? This means that on average, 200 people move away from this town per year. it's negative, so that's going to be a declining, right? So we might say the population decreases, let's abbreviate that, decreases by 200 people each year. Okay. If the population had been increasing, the slope would have been positive, right? We would have been adding 200 people each year, but in this case, it was decreasing. So 200 people were leaving, or we were subtracting 200 people from the population every year. So it was negative. All right, probably enough about slope for now. Let's move on to writing linear equations. All right, when we write a linear equation, there are three forms that equation can take. The first and by far the most useful form is the slope-intercept form. Y equals mx plus b, where m is the slope of the line, or the rate of change between 2 points on that line, right? And b is the y-intercept, or where that line intercepts the vertical axis, the y-axis. In an application or in context, a linear function, the slope is rate of change, then the y-intercept, or this b, is thought of as the initial value of the function, the initial value of the function. So in our population example, we didn't know anything before 1990, so we would have thought of 1990's population of 60,000 as our initial value. All right, another form that is used sometimes is the point slope form. The point slope form says y minus y1 equals m times x minus x1, where x1 and y1 are the coordinates of a point that's on that line. There is a third form that isn't very valuable, but you will sometimes see, and that's the general form. The general form says ax plus by equals c, where a, b, and c are just constants, or I'm sorry, just values. All right, let's look at some examples. Okay, let's come back to slope for a second. If we have an equation, and it's not necessarily written in any specific form, and we want to find the slope of that equation, the best form to use is this slope-intercept form. Look, if all we have to do to put an equation in slope-intercept form is solve for y, and if we have solved that equation for y, or we have y all by itself on one side of the equation, then the slope is going to be the coefficient of the x, or the number in front of the x. So if we look at this example here, just write this up here, so we say y equals mx plus b, our slope-intercept form. This isn't in the right form now. If I wanted to look at for the slope, and I looked in front of the x, I saw the coefficient there was a 1. I could not say the slope of this line is 1 because it's not in the right form yet. It's not. We haven't solved for y, or we don't have y all by itself on one side of the equation. If we solve for y, then we'll easily be able to determine the slope. We'll just look at whatever the coefficient of the x is. All right, so let's go ahead and solve for y. We'll subtract an x from both sides. So then 3y is equal to negative x plus 33. And then we don't 3y, we just want y, so we'll divide everything by 3. So then y equals negative x divided by 3, or we could write that as negative 1/3 x plus 33 divided by 3 is 11. Okay, now this equation is in slope-intercept form. We've solved for y. Y is all by itself on one side. Now we can see that the slope, m, is going to be the coefficient of the x term, number in front of the x. So we can now easily say here that the slope of this equation is negative 1/3. All right. Look at this example over here. I might be tempted to say the slope is negative 6, but it is not in slope-intercept form, so I can't do that. But if I solve for y, it'll be in slope-intercept form. Then I can just look at the coefficient from the x. So let's solve for y. We'll add 6x to both sides first. So then negative 4 y is equal to 6x plus 25. And then we'll divide everything by -4. So then y is equal to negative, or 6 over -4, which will reduce to 3 over -2, or -3/2 x minus 25/4. All right, now that we solve for y, we can see that the slope is that coefficient from the x, or -3/2. What's the slope of this guy? Oh, that's so weird. There's no x in there, is there? Well, one thing I could do is I could say, well, if I wanted to write this in slope-intercept form, I could say that y equals 0x plus 2, right? That's the same as y equals 2, because 0 times x is 0, and it just goes away. Well, if I write it that way and I think about it that way, I can see here that my slope is equal to 0, right? I can't do that with this guy, though. This one is really weird. This one is really weird. Well, think back when we were looking at slope. See if I can find that page real quick. To get myself out of order here. When we were looking at slope and we found one where the x coordinates were the same and then the y coordinates were the same. I said if the x coordinates are the same, it's a vertical line. If the y coordinates are the same, it's a horizontal line. Well, we don't know 2 points in this case, but we knew that when we found that the y coordinates were the same, it had a slope of 0, right? So that means this guy, he's going to be a horizontal line. Well, when we don't know anything at all about the y, just that x is always -1, think about how that might look graphically. -1 is there. If x is always -1, regardless of what y is for any coordinates on that, if we were to graph that, look what we have here, a vertical line. This one is a vertical line, so the slope is undefined. It's undefined, and that's a vertical line. Okay, sometimes, even though the concept might not seem that complicated, sometimes it's easy to get these mixed up. So there's an acronym. We have lots of acronyms in algebra, don't we? But there's an acronym here that helps us remember that vertical lines have an undefined slope, and the equation is in the form x equals some constant. Okay, so Bucks-Hoy is an acronym that we can use to help remember these details. Vertical lines have undefined slope. The equation is in the form x equals a constant. The Hoy portion of Bucks-Hoy says horizontal lines, H for horizontal line, has a slope of 0. Okay, we're taking a little liberty here, O and 0. But the equation then is going to take the form y equals some constant. All right, so Bucks-Hoy, vertical line has an undefined slope, x equals some constant. Hoy, horizontal line, has a slope of 0. Equation equals y, or the equation is y equals some constant. So, given that, let's see if we can write some equations when we don't necessarily know everything about a line. All right, so what do we have in these examples here? The first one says the equation of a line. We need to find the equation of a line that has a slope of -3, and it contains the point 0, 5. All right, so they're telling us the slope. It's -3, so m is -3. They tell us this line contains a point, so there's an x1 and a y1. Well, let's see. If we use, well, slope-intercept form was pretty valuable, y equals mx plus b. Can we use that to write the equation of the line that goes through this point 0, 5 and has a slope of -3? Well, the slope part's going to be easy, right? We can say y equals 3x, but what about that y-intercept, that b? Right, because remember, b is the y-intercept when we graph it, or it's the initial value in an application. How do we go up find that b? Well, you might notice something here, right? Remember that if the x-coordinate is 0, that point is going to lie on the y-axis, right? Think about if we graph that point. Graph that point. X is 0, y is 5. So when we graph that point, there it is. It's like that, right? So actually, if we remember that, we can look at this point and we can know that b is 5. Our y-intercept has the coordinate 0, 5, right? So that means b has to be 5. But what if we just didn't think about that when we were looking at that? Would there be another way to find out what that b is? Could we still use the slope-intercept form? Sure, we could still use the slope-intercept form. But what we'd have to do is use this point to find b, right? So the other thing that we could do is we could substitute the x and the y values into my equation y equals negative 3x plus b, right? So 5 equals negative 3x, x is 0, negative 5 times 0 plus b, and then just solve for b. Well, negative 3 times 0 is just 0, so b equals 5. So there's a second way we could do that. Is there a third way? Well, remember, we had 3 forms we could write the equation, and the general form doesn't really help us, but we also have this point-slope form, right? This point-slope form says y minus y1 equals m times x minus x1. So if we don't know the y-intercept, we might be able to use this point-slope form to write the equation for the line. All we would need to know is the slope and one point that's on the line. Look at the second example here. We do know the slope, it's 1/2. In the second example, find the equation of line with the slope of 1/2, and it contains the point 2, negative 3. So we know an x1 and a y1. Well, I can just plug these values into the point-slope form for the equation of a line and solve for y, and then I'll have my slope-intercept form. Let's do that. So y minus y1, well, that's going to be negative 3. So y minus negative 3 is equal to m, the slope, that's 1/2, times x minus x1. x1 is 2. All right? Well, y minus negative 3 is y plus 3. And then let's simplify that right-hand side. We'll distribute that 1/2. It's y plus 3 equals 1/2 x minus 2 times 1/2, which of course is just 1. Solving for y only requires one more step. Subtract the 3 from both sides. So then y is equal to 1/2 x minus 4. So that was easy for this guy. All I have to do is plug and then solve for y. I could have also solved the second example here starting with my slope-intercept form and using that point for the x and the y. Let's try it that way. Should get the same equation, right? With the slope-intercept form, y equals m. I know that. It's 1/2 x, but I don't know what b is. But I can use this point to find b, right? So I'll go ahead and substitute. I'll substitute the negative 3 in for the y, the 2 in for the x, and then I'll just solve the b. So negative 3 plus 1/2 times, negative 3, I'm sorry, equals, no, I wrote plus, negative 3 equals 1/2 times 2 plus b. So negative 3 equals 1/2 times 2 is just 1 plus b. When I subtract that 1 from both sides, I see that b equals negative 4. I can then just substitute that back into my equation, and y equals 1/2 x minus 4. Same equation. Okay, so multiple ways to solve these. multiple ways they all get us there. Let's get a couple more examples. What do we notice about these? Look, this first one, the x coordinates are the same. Well, if the x coordinates are the same, the change in x is 0, right? So that's a divide by 0 situation when I plug it in, isn't it? If I were to find the slope, I would end up with a 0 denominator. Okay, so I might notice by looking at the 2 points, well, if x is -3, when y is different values, it doesn't really matter what the y values are. I can just write my equation, x equals -3. Right? That's going to be a vertical line. But if I hadn't noticed that, I could go about this the same way that I was doing the last examples. I don't know the slope, but I could calculate the slope, right? I could calculate it. Let's see what the slope is. I might remember that, oh, that's a divide by 0, it's undefined, right? But if I didn't, I could do y2 minus y1 over x2 minus x1. I'd get 3 over 0, and then I'd remember, oh, yeah, can't divide by 0. That's an undefined slope. An undefined slope, I think about that acronym, VUX-HOI, undefined slope, applies to the VUX part, undefined. Vertical line has an undefined slope, has an equation, x equals some constant. Okay, in the second example here, the y's are the same. They're both 5. The y's are the same. Well, I might remember that means that that's going to be a horizontal line, right? If I also might notice, okay, y's are the same even when the x's are different, so that must mean that's an equation, y equals what the y always is, y equals 5. Okay. But, I could also go ahead and use this slope formula, right? I could use this slope formula and say that m is y2 minus y1, that's 5 minus 5 over 8 minus 3, x2 minus x1, 0 divided by 5, that's of course 0. All right, slope of 0 applies to the HOI portion of VUX-HOI, our little acronym to remember. Horizontal line has a slope of 0. Equation is y equals some constant, y equals 5. All right, various ways to think about this. Let's look at one more example. One more. Look at this guy. Find the equation of the line that goes through the points 4, -8, 36, -32. All right, well, there's nothing I can determine about this on observation, right? I don't have any x's. The x's aren't the same, the y's aren't the same. So it's not going to be a vertical line or a horizontal line. None of the coordinates are 0, right? So that's not going to help me. So what do I need to do here? Well, to write the equation of a line, I need to know 2 things. At a minimum, I need to know the slope and at least one point that's on that line. I'm not given the slope, but I can certainly calculate it. So why don't we start with that? Let's calculate the slope. y2 minus y1 here. Here's an x1, here's a y1, an x2, and a y2. Okay, y2 minus y1 is going to be -32 minus y1 is -8. Okay, divided by x2 minus x1, that's 36 minus 4. All right, so -32 plus 8 is going to be -24. And then 36 minus 4 is going to be 32. All right, that will reduce, of course, that reduces down to -3/4. 8 goes into -24 3 times, -3 times, and 8 goes into 32 4 times, or my slope here would be -3/4, right? Because -3 over 4, of course, is the same as 3 over -4, which is the same as -3/4. So there's my slope, but I don't know the equation yet, right? I know that y equals -3/4 x plus b, but I don't know what b is. I don't know what that y-intercept is. Well, I can use one of the points to find the y-intercept, or I could use both of the points and the slope in the point-slope form. I think I'll just use one of the points. These look like nice, easy, low numbers. So I think I will just plug in -8 for the y. That's going to be -3/4. And I'll plug in the 4 for the x. These 4's then divide out. So -8 is equal to -3 plus b. That would be b. Add 3 to both sides, and I have my value for b. B is going to be equal to -5. All right, so I can then put that in there for b, and I know my equation now. Y equals -3/4 x minus 5. Okay. All right, let's look at a few applications. All right, here we have a phone salesperson. They're paid a salary with commission on every phone sold. All right, the pay in dollars, P, is given by this, is determined by the formula given. Okay, so P is equal to 15x plus 330. All right, where X is representing the number of phones sold. All right, so what are they saying there? They're saying this person gets $330 pay every week, even if they don't sell any phones. But for every phone they sell, they get an additional $15. My rate of change here is that additional $15, right? What is the initial value? Well, the initial value in this function is the base salary, right? This is base salary plus commission. So the initial salary is going to be the $330. Okay, what does it mean in context? It's the base salary. It's the salary that is earned even if no phones are sold. Okay, what is the rate of change in this function? Well, the rate of change, well, the slope, we know that slope, right? Is this in slope-intercept form? Oh yeah, it's function notation, P, but P, that's like our Y, right? MX plus BM is our 15. So what is the rate of change? 15. Well, what does that mean in context of the problem? That means an additional $15 is earned every time an additional phone is sold, right? So let's see. 15 earned for each phone sold. All right, let's look at another application. All right, so at 8 a.m., the temperature was 64 degrees. By 4 p.m., the temperature had gone up to 86 degrees Fahrenheit. What was the average rate of change of temperature between 8 a.m. and 4 p.m.? All right, so it maybe didn't go up steady, but we're only looking for an average rate of change. Sounds to me like we want to use the slope formula, right? Because slope is rate of change, right? M equals the change in the y's over the change in the x's, right? Sometimes we think about it this way, right? Delta y, the change in the y's or the change in the x's. So what are my x's and y's here? Well, the x is an independent variable. The y is the dependent variable. So given an x, what is y? Well, given a time, we can determine the temperature, right? Given at 8 a.m., the temperature was 64 degrees. Given at 4 p.m., the temperature was 86 degrees. So it sounds like my x's are the times, and my y's are the temperatures, right? So I think I might be able to write 2 points here. There's something weird going on with this time, right? There's something weird going on with this time. If I wrote these points like this with the coordinates of 8 a.m. and 64 degrees and 4 p.m. and 86 degrees, and if I tried to calculate the slope with them using the time, I'm not going to get the right. I'm not going to get the right value, am I? I'm not going to get the right value because I'm interested in the change in time. So I could use military time. If you're familiar with that, in military time, 8 a.m. is 8, and 4 p.m. the afternoon hours add to 12 noon. So in military time, 4 p.m. would be, let's see, noon is 12, 1 is 13, 2 is 1400, 3 is 1500, 4 p.m. is going to be 1600 in military time. So if I used military time, I'd be fine. Or I could just use my thoughts here, or use my interpretation of rate of change as the change in the outputs, or the change in the temperatures over the change in the inputs, or the change in the times, right? Or the change in the dependent variable, temperature, over the change in the independent variable, time, right? Well, if I thought of it that way, I'd say the change in the independent variable, or dependent variable, sorry, the y's, is going to be 86 minus 64. The change in the x's, I don't want to say 4 minus 8, do I? No, I'm going to end up with some negative temperature, and we see the temperature rising. It's not going to apply. I could say 16 minus 8, though. I could use the military time, right? Or I could just calculate what is the change in time here. Let's see, from 8 o'clock, 9, 10, 11, 12, 1, 2, 3, 4. I'd see that the change in time is 8 hours. So we have 86 minus 64 over 8, the change in time. 22 divided by 8, and if I wanted to write that as a decimal, uh-oh, where'd my calculator go? Oh, there it is. Old one. Hopefully this one will work. Let's see what that is. 22 divided by 8. 2.75 degrees per hour. The rate of change is always a change in something over something else. The rate of change is in temperature, or degrees per hour. Okay. All right, let's move on to graphing linear functions, or graphing lines. When we graph, basically 3 ways we can do it. We can generate a table of values. I just had a problem with my computer. Let me fix that real quick. Okay, we can generate a table of values and then connect the points. That will give us the line. We could look at the line and slope-intercept form and start with the y-intercept and then just count out rise over run with the slope. Or we could find the x and the y-intercepts and then connect those points. Because, you know, to graph a line, we really only need to know 2 points. Right? Let's try with the first method, graphing from table of values. We just need to pick some x's and calculate the y that goes with that x to make the equation true. Right? So, I don't know, say x is 0. If x is 0, 0 plus what equals 10, y would have to be 10. Right? Well, those are the coordinates of 1 point, 0, 10. Those are the coordinates of 1 point on this line. So I could plot that point. X is 0, y is 10. That's that point up there. Right? Let's see. I don't know. Let's see. What happens when x is 3? When x is 3, 3 plus what equals 10? 3 plus 7 equals 10. So there's the coordinates of another point. 3, 7. Right? X is 3. I'll plot that one. 1, 2, 3. Y is 7. 1, 2, 3, 4, 5, 6, 7. Here's the second point. And I really only need 2 points, but maybe I'll find a few more just to make the sketch easier. How about if x is 7? Well, 7 plus 3 is 10, then y would have to be 3. So there's a point I could plot. X is 7, 5, 6, 7. Y is 3. There's a point. How about if x is 10? Well, if x is 10, y has to be 0, right? That's that point there. So there's the graph of my line. All I need to do is connect these points. Even though I didn't need all 4, I went ahead and did it. I really only needed 2 for a line. When we start graphing nonlinear functions, we might need more than 2 points, but there we go. There's the graph of that line. It's important to note that each point on this line is a solution to that equation, right? Each point on this line, the x and y coordinates of that point, make that equation true. All right, a second way to graph lines is using the slope-intercept form. If we have an equation in slope-intercept form, we know a lot about that equation, right? B, if it's y equals mx plus b is the form, m, our slope, is the coefficient to the x term, right? Or in this case, -1/2, okay? And then b is the y-intercept, right? B is the y-intercept. So in this case, we see that 3 is the y-intercept. This line intercepts the y-axis at 3, right there. So I can plot that point and start with that. Of course, the coordinates of that point are 0, 3. And I can use this slope in a rise over run form to count out and find the second point, right? So m is -1/2. Well, I could write that as -1 over 2, or I could write that as 1 over -2. That's the same thing, right? And if that's my rise over my run, if I start at this point, the next point, using maybe 1 over -2, the rise would be +1, so I go up 1. Run is -2, I go to the left 2. There's another point that's on that line. Okay? I could do it again if I wanted more than just these 2 points, up 1 to left 2. In fact, I could keep going if I wanted several to connect. Maybe didn't have a straight edge. I could also use the slope as in this form of -1 over 2, right? If I had done that, my rise is -1, so I go down 1. My run is +2, so I go to the right 2. I could do a few more if I wanted to, down 1 over 2. Okay, and there's the graph of my line. Okay, using the third method, I want to find the x and the y intercepts and then connect them for the graph of my line. So think for a minute about where this line will intercept, say, the y-axis. This line's going to, at whatever point this line intercepts the y-axis, the x-coordinate of that point is going to be 0, right? Because all the points on this y-axis have an x-coordinate of 0. So wherever it intercepts, the x-coordinate is 0. So to find that y-intercept, I can just plug 0 in for x and solve for y. Because I know that that point will satisfy that equation, or make it true. So when x is 0, 2 times 0 plus 3 times whatever y is that goes with that on this line. And 2 times 0 is just 0, so 3y equals 6. Well, if I divide both sides by 3, I see that y equals 2. So the y-intercept is going to occur at the point 0, 2. Right there. There's our y-intercept. 0, 2. Okay, the x-intercept, all the points on the x-axis have a y-coordinate of 0, right? That point has no vertical displacement. So the y-coordinate is 0. So I should be able to substitute 0 in for y in the equation and solve for x. And that'll give me my x-intercept. So 2x plus 3 times 0 equals 6. So 2x equals 6. When I divide both sides by 2, I see that x equals 3. Okay, so that means my x-intercept has the coordinates 3, 0. Right there. And that's all I need to graph this line, are those 2 points. Kind of close together, so I have to be careful with my straight edge. But that line is going to look like this. Okay. Now, horizontal lines, y is 3, y equals 3 is a horizontal line. Remember, Buck's hoy, y equals 3. It has a slope of 0. Well, to graph it, we just want to find where y equals 3, maybe on the x-axis. But when x is 0, y is 3. But y is always 3 here, regardless of what x is 0. All these other points are going to be on here. It's going to be a horizontal line right there. The other way to think about that is with Box-Hoy, horizontal lines. Horizontal has a 0 slope. The equation is y equals, in this case, it was y equals 3. Okay, for a vertical line, that's the Box portion of Box-Hoy. Vertical line has an undefined slope, has the equation x equal -2. Okay, so x is -2. Let's see, x is -2 on the x-axis right there, but I don't care what y is. X is always -2. Y can be all kinds of whatever. It's going to be a vertical line right here at x equals -2. All right. One more example involving horizontal and vertical lines. Find the equation of the horizontal that goes through the point 3, -4. All right, where's that point? Let's plot it. Let's look at it. X is 3, y is -4. So there's the point right there. Point is 3, -4. So the horizontal line, we'll go ahead and graph it. It's this guy here. The vertical line is this guy here. Now I can think about Box-Hoy to find my equation. Or I can just say, well, gee, on the horizontal line, the y is always -4, isn't it? The x changes, different points on that line. I didn't do that, I did a +4. Here, let's just change it. We're going to say it's 3 +4, because I graphed it wrong. There, 3 +4. So, so the y coordinate of every point on that line is going to be a +4. Like this point right here, it has the coordinates -5, +4. This point here has the coordinates x is 0, but y is +4. Okay, so I could use Box-Hoy for that horizontal line, y equals 4. Or I could graph it and look at it and say, oh, well, all the y's are always 4. I don't care what the x's are, so y equals 4. Okay, the vertical line here, if you look at this vertical line, every point on this vertical line has an x coordinate of 3. This point here on the x-axis is 3, 0. This point down here has the coordinates 3, -5, right? So that means that I don't really care what y is, but x is always 3. One way to think about that. Or I could say it's a vertical line, use the Box portion of Box-Hoy. Vertical line has undefined slope, and the equation is x equal some constant. In this case, the x is 3. Okay. The intercepts of horizontal and vertical lines are always going to have one of the coordinates to be 0, right? Here we have x equals 4. That, of course, is a vertical line, right? A vertical line. And it intercepts the x-axis at 4, but the point itself, the intercept itself, has the coordinates 4, 0. Right? If I were to graph that line, x equals 4, there's the line right there. Okay, the intercept right here, it has an x coordinate of 4, right? 1, 2, 3, 4, and the y coordinate is 0. For horizontal lines, y equals -2. If I were to graph that one, there's y equals -2 right there. The intercept occurs when x is 0 and y is -2. So the coordinates of that point, or that intercept, would be identified as 0, -2. All right, let's talk for a minute about parallel and perpendicular lines. They have special relationship. Parallel lines have the same slope. Perpendicular lines have slopes that are opposite reciprocals. What does that mean, opposite reciprocals? Opposite means they have opposite signs, right? So the slope of line 1 is going to be negative the reciprocal of the slope of line 2. So the reciprocal is the number that you multiply something by to get 1, right? So the reciprocal of M2 would be 1 over M2, because 1 over M2 times M2 is equal to 1, right? So let's look at this next page. It has a nice summary here. What are parallel lines? Parallel lines, of course, are like railroad tracks, right? They're lines that never intersect, and the slope of those lines is equal. The measure of slantedness on that line is going to be equal, or the rate of change on that line is going to be equal. So M1, the slope of line 1, is equal to M2, the slope of line 2. Some examples of equal slopes. Perpendicular lines are a little more complicated. Perpendicular lines, of course, are lines that intersect at a 90-degree angle, right? Lines that intersect at a 90-degree angle, and their slopes are opposite reciprocals. Or the slope of one line is going to have the opposite sign. So look, if this was line 1 here and this was line 2, the slope of line 1 would be positive because it's slanting upward. Upward slanting lines have a positive slope. The line slope 2 is going to be negative because it's slanting downward, right? And then the value of the slope of line 1 is going to be opposite. It's going to be the reciprocal line 2. So here's some examples. For line 1, if the slope of line 1 is 1/3, the slope of line 2 would be negative the reciprocal of 1/3. And the reciprocal, one way to think about the reciprocal is it's just a fraction that's flipped, right? But when I multiply 1/3 by 3 over 1, I get 1. That's what makes them reciprocals. Okay? If the slope of line 1 was 5, then the slope of line 2 is going to be negative 1/5. Now 5 as a fraction is 5 over 1, right? So to find the reciprocal, I flip the fraction, 1/5. Of course, then it's the opposite. So if the slope of line 1 is negative 2/7, the slope of line 2 then is going to be the opposite sign of negative, or positive, flip the fraction, positive 7/2. Okay, let's look at some examples. Determine if the following pairs of lines are parallel, perpendicular, or neither. All right, so remember, parallel lines have the same slope. Slope of line 1 equals the slope of line 2. Perpendicular lines have slopes that are opposite reciprocals. So the slope of line 1 is equal to negative 1 over slope of line 2. Or I could think about this way. I could say the slope of line 2 is equal to negative 1 over the slope of line 1. Let's say the same thing, right? So it looks like if I'm to determine if these two equations are parallel, perpendicular, and neither, I need to know what the slopes are, right? So I can compare those slopes. Well, the easiest way to determine the slope of an equation is to solve for y. Put it in its slope-intercept form, y equals mx plus b, because then the slope is going to be the coefficient of the x. So let's do that. Solve for y. And for this first equation, all I have to do is subtract a 6x from both sides. So then y equals negative 6x plus 7. All right, let's do it for the second equation. Solving for y, well, I'll have to subtract the 6x from both sides. I'll have to do that. We'll subtract the 6x from both sides. So then I'll have negative 36y equals negative 6x plus 14. Then I'll need to divide everything by negative 36. Another room, so I'll finish up there. Let's divide out. So then y is equal to, and negative 6 over negative 36 will reduce to positive 1/6, right? Negative over negative makes it positive. 1/6 x minus, and then 14 over 36 reduces to 7 over 18. All right, so here's my two equations. Let's compare the slopes. When the slope of the first equation is negative 6, when I solve for y in the second equation, I solve the slope is positive 1/6. Are they parallel, perpendicular, neither. Well, they're not parallel because -6 is not equal to 1/6. Are -6 and 1/6 opposite reciprocals, right? So so if M1 is equal to -6 and M2 is equal to positive 1/6, does M1 equal -1 over M2 or M2 equal -1 over M1? Well, let's see. I could think about that either way. Let's do it the harder way. Let's see if M1 is equal to 1 over M2. So does -6 equal -1 over positive 1/6? Oh, that's weird, isn't it? That's a compound factor. Let's simplify that. If we have 1 divided by -1/6, that's kind of like, let's do it up here. That's kind of like 1 over 1, right? -1 over 1 divided by 1/6. So that's a fraction divided by a fraction. Remember how to divide fractions? You keep that first fraction, change the sign to multiplication, and then flip the bottom fraction. Change, flip. Some of you might have learned that. Then when we multiply them, we get 6 over 1. Of course, it's negative, or -6. So look at this. -6 does equal -6. It's true. So what does that mean? That means that these are perpendicular because M1 equals -1 over M2, right? So I'd say perpendicular. Perpendicular because M1 equals -1 over M2. -6 is equal to -1 over 1/6. Now, this was easier to do M2 equals -1 over M1, but it doesn't matter. They're both going to say the same thing. If we looked at it this way, we would have said 1/6 equals -1 over -6, which of course would be 1/6. So they're perpendicular. What about these second two equations? Well, let's solve for y and compare the slopes. See, so for the first equation, we'll just subtract a 2x from both sides. So 4y will be -2x plus 2, and then divide everything by 4. So then y is equal to, let's see, -2/4 reduces to -1/2 x plus 1/2. Okay, so my first equation has a slope of -1/2. Let's see what the second equation slope is. Here, I think we just need to divide everything by 3 to solve for y. So then y equals, oh, look at this, -3/2 divided by 3 minus 6 divided by 3. That's just 2. Okay, this is weird. X from X. -3/2 divided by 3. Well, we got to simplify that, right? That's like -3/2 divided by 3 over 1. Okay, so if we keep, change, flip, then we have -3/2 times 1/3, or -3/6, which of course reduces down to -1/2. Okay, so y equals -1/2 x minus 2, and -1/2 is equal to -1/2. They're the same. In this case, M1 equals M2, so these are going to be parallel lines since they have the same slope. Now, if we ended up with maybe -1/2 and positive 1/2, we'd have to say neither, right? Or if we ended up with maybe -1/2 and 3, we'd still have to say neither, right? Because they aren't equal and they aren't opposite reciprocals. Let's look at 2 more examples involving parallel and perpendicular lines, looking at it from a little bit different angle. So this first example is find the equation of the line parallel to y equals -3/5 x minus 6 and goes through the point 5, 4. Right, well, if this equation is parallel, right, that means the slopes are equal. So, and I know this is already in slope-intercept form, so I know that the slope of the first line is -3/5, so that's going to be the slope of the line that I'm looking for, right? -3/5. So I know the slope, I know it, it's negative 3/5. I know one point that is on that line, it goes through to the point 5,4, there's an x1 and a y1, right? So I could use point slope form here, or I could just say, well, let's see, y equals m, I know that now, 3/5 x plus b, and I could use this point to find b, right? Let me just substitute 4 in for the y and 5 in for the x. So then 4 equals negative 3/5 times, put x in for 5 plus b, and these 5's divide out. So, so then I have 4 equals negative 3 plus b. I'll just add that 3 to both sides. B, why did I write a 5? B. I'll add that 3 to both sides, and I'll see that b equals 7. Now I can write the equation in my line. Y equals m, negative 3/5 x plus b, which we just found was 7. Right? What if I needed to find the equation of a line perpendicular to another line? Well, remember the relationship of those slopes. The slope of line 1 is equal to negative, reciprocal, or negative 1 over the slope of line 2. So I think my starting point here, and it goes through this point 3,4. So I've got an x1, y1, but this is not in the right form to determine the slope. So let me solve for y, put it in slope-intercept form, and then we'll know what the slope is. All right, so let's subtract a 2x from both sides. So then 4y is going to be negative 2x plus 2, and divide everything by 4. So y is equal to negative 1/2 x plus 1/2. So my slope of the given line is negative 1/2. So if the slope of the given line is negative 1/2, what is the slope of the line I'm looking for? Or my m2 have to equal to opposite sign, so it's going to be positive, right? It's going to be positive, opposite reciprocal. The reciprocal, what do I multiply 1/2 by to get 1? I multiply it by 2, right? So it's going to be positive 2 is my slope, all right? So now that I know my slope, I can find the equation of that line. I could do it like I did above, using this point to substitute in for x and y to find b, or let's do it the other way. Let's use the point slope form, right? What is that? Y minus y1 is equal to m times x minus x1. Let's do it the other way this time. So y minus y1, so y minus 4 is equal to m. We just found that to be 2 times x minus x1, that's 3. Okay, let's simplify. Distribute that 2. So y minus 4 equals 2. Oops, that's minus. Sorry. Y minus 4 equals 2x minus 2 times 3, or 2x minus 6. Now we'll just add that 4 to both sides. And we'll see that y equals 2x, and then negative 6 plus 4 is going to be minus 2. There's the equation of the perpendicular line to 2x plus 4y equals 2. Okay. All right. We're almost done here. Let's wrap up with a couple of applications. Coming back to writing linear equations. All right, so here we have, last year, Pinwheel Industries introduced a new toy. It cost $5,500 to develop the toy, and then $40 to manufacture each toy. Okay, all right, so let's see. Now, this is a linear application, right? So it's, part 1 says, give a linear equation in the form C for cost equals m, slope, or rate of change, times n plus b, where C of cost and n is how many toys we're producing, right? Well, let's see. Linear equations have an initial value, right? That's my y-intercept, or my starting point. And then they have a rate of change, or a part of the equation that changes, based on the slope or the rate of change. So if I'm looking at this equation, C equals mn plus b, it looks like b, that's my initial value, right? That's my starting point. Graphing this, that would be my y-intercept. M is my rate of change, n is how many toys I'm producing, okay? So what is this equation going to look like then? Cost is going to equal to m, slope. Slope is rate of change, though, in context, right? What is the rate of change in the costs here? Well, it says it's $40 to manufacture each toy. So it looks like 40 is my rate of change. So 40 times the number of toys that we're manufacturing, and then plus my initial value or my starting point. This is a cost equation, right? So the initial cost is that $5,500 that was required to develop the toy. So what is the total cost then to produce n equals 2,600 of these toys? Well, all I'm going to do is I'm going to substitute how many toys I want to produce into my cost equation. And that will give me that total cost. So cost is going to equal 40 times 2,600 plus the 5,500. Okay, so there's that. 40 times 2,600 plus the 5,500, $109,500. Part 3 says how many toys can be produced with $189,500. Okay, so our cost budget here is $189,500. How many toys can we make and not spend $1 more, right? Well, that means that C is equal to the $189,500. So what I want to do is I want to substitute that in there for C. So I want to say cost, $189,500 is equal to 40N plus the 5,500. And if I solve for N, that's going to tell me how many toys I can manufacture. Right? So I'll start by subtracting that 5,500 from both sides. Kind of out of room, so I'll write it over here. 189,000 minus 5, so that's going to be 184,000 is equal to 40N. We'll divide both sides by 40. And I'll see that I can produce 184,000 divided by 40, 4,600 toys. So n equals 4,600 toys. Sorry about that, my phone is ringing. Okay. Let's look at another application. You can relate to this one. Here we have a college algebra student. They have, let's see, oh, this is similar to the one we did before, right? We have test scores of 78, 82, 61, and 91. Okay, so there's 4 test scores, each out of 100 points. Okay, then the final exam is out of 200 points. 200 points. What is the lowest grade the student can get in the final, on the final, to a B or an average score of 80 in the course? Well, an average, usually to find an average, we add up all the test scores and divide by how many there are. But for this example, that final, it's a little bit of a problem because it's not on an equal ground with those tests, right? Each of the 4 tests were out of 100 points. The final is out of 200 points, right? So there's a couple ways to approach this. Probably the easiest way, though, is to think about that final as being worth 2 tests, right? Or it being like a double test, if you will. Okay, so one way to set this up would be, okay, we need it to be an average of 80, right? So we need to equal 80. Okay, an average is add up all these test scores and divide by how many they are. So that'd be 78 plus 82 plus 62 plus 91 plus, I don't know the score on that final exam, so we'll call it X. But if that's going to be worth 2 tests, because it's out of 200 points, right? Out of 200 points, then I might call that 2x. It's like 2 tests, right? That's one way to do this. Then I divide by how many tests there are, 1, 2, 3, 4. But if that final exam is worth 2, then I'm going to have to divide by 6, not 5, right? Okay, so if we multiply both sides by 6, that 6 will divide out. Let's see, let's add up, let's simplify that left-hand side. 78 plus 82, off the page here, plus 62 plus 91. All right, so that's 313 plus 2x is equal to 80 times 6, that's 480. And we'll subtract that 313 from both sides. So then 2x is equal to 167. And if we divide both sides by 2, we see that x has to be 83.5. Okay, this person needs to score at least an 83.5 on that final exam to bring their grade up to an 80. So that's one way to do this. Another way would be to think about these as percentages, right? To think about these as percentages. A little bit more complicated though. So I really think this is probably the most direct approach to take. One more application. All right, let's see what's going on here. An athlete begins normal practice for the next marathon during the evening. He begins running at 6 p.m. and he finishes his run at 7:30 p.m. Over that time, that hour and a half, he's run 7.5 miles. All right. First part of this application says write an equation representing the distance that runner has gone over time in hours since 6 p.m. And time is going to use the variable t. Okay, and distance will use the variable d. Well, the starting point here is to remember that distance is always equal to the rate times time. Right? The rate, how many miles per hour, or how many feet per second, or some rate times the number of time, amount of time. So for this particular athlete, the distance is going to equal the rate, okay, we don't know what that is yet, times time, and they want us to use t for time. So how do we find out that rate? Well, a rate is what? A rate here is how far he ran over time, like if he's running 5 miles per hour or 10 miles per hour. So in this case, the rate is, let's put it that way. In this case, the rate here is going to be how far he ran over the amount of time, right? We could use this equation even to solve for rate, right? If I divide both sides by t, I could say that rate equals distance, or d, over time, right? Distance over time. Well, how far did he run? He ran 7.5 miles. Okay, so there's my distance, 7.5 miles. How long did he run? He started at 6 p.m. He ended at 7:30 p.m. We want our time to be in hours. How many hours was that? It's 1.5 hours. So his rate then is 7.5 divided by 1.5, or 5 miles per hour. So there's the rate. So next part says how many miles did he run in the first 45 minutes? Well, I can use my equation for distance to find out how many miles, because that's a distance, right? So that distance is going to be the rate, that was 5 miles per hour, we just found that, times how many hours? 45 minutes. Well, 45 minutes in hours, let's see, that's not a full hour yet, right? It's 5 minutes out of an hour. So 45 over 60, that's going to reduce down to 3/4 of an hour, right? Or 0.75 hours. Okay, so 5 times 0.75 is 3.75 miles. Okay, if he kept running at that same pace for a total of 4 hours, how many miles will he have run? How many miles? Well, if the rate is 5, we want to find out how many miles again, so we can use our formula. Distance, how many, is equal to rate. My rate, we found, was 5 miles per hour. The time, now we want to find out how far he would run for 4 hours. So 5 times 4, that's going to be 20 miles. 20 miles. Okay. This ends the lecture on linear equations in 2 variables.